So now we have a model of halo abundances. We have a model for the halo distribution because we have a bias factor as a function of halo mass. And if we multiply by the dark matter clustering, we have the halo clustering. Yeah? And so now we'll put this together in the halo model. Okay, so what's the goal? So the goal is clustering is a function of galaxy type. In this case, the red are the luminous, and the blue or the light green, they're the less luminous galaxies. Now the red is red galaxies, the blue is blue galaxies. So all these are different point processes that are tracing the same underlying dark matter distribution. And so that means that not all galaxies are fair tracers of the dark matter, because only one of those types can be. And so our goal is to try to infer the distribution of the mass from the distribution of the light that we see. Yeah? And we know that the distribution of the light is biased. And so we want to understand this bias. We want to account for this bias. Oh, I have some of these quotes from, there's a famous, not cricket coach, but a baseball coach. And he said many things that are a little bit crazy, but when you think they're also a little bit clever. So I'm a theorist, so for me it's good to remember that you should look at the data. Okay? And so our goal is to describe point processes which are built from the same underlying density field, which should be the dark matter. Yeah? And so the halo model is the language for doing that. And it's a language that was first written out in 1952, so a long time ago. Okay? By this guy called Jerzy Neyman and a woman called Elizabeth Scott. And Neyman was someone who was, so a statistical lab, so he was a statistician. His job was in Ukraine, I think, where he was measuring the sizes of potatoes to see if the crop was as good as it could be, this kind of thing, to each year to keep some statistics. It was in the 20s or the 30s, and there was some interest in Fisher information matrix was just doing that stuff. This Bayesian frequentist was going on. So Neyman said, I want to go and I want to do that, the formal statistics rather than the practical statistics. Okay. So the people said, we don't understand any of this formal stuff. So you can go to England and you can study it. And if you write a paper with the guys there, then we know that you are good enough. Then you can come back to your job. So he went to England and he never wrote a paper with the guys there. But he developed a lot of stuff. So he never went back. Instead, he went in the end to Berkeley to start the statistics department in Berkeley. And there he met Elizabeth Scott. And one of the things that they did was this model. So for Elizabeth Scott, there was a bunch of data that was just coming online of sky surveys where a bunch of galaxies were dots. And so they were people were beginning to measure the clustering of the dots. And so the question was, what is a good way to describe this set of dots? And so they came up with what is now called a center-satellite process. So the idea is you have a cluster center with some galaxies around it. Then you have another cluster center with some other galaxies around it. And you want somehow to describe this thing. Okay? So what are the things that you need to describe this process? Okay? They said, well, you need to know how many big dots and how many big groups and how many small groups. So in modern language, we will call that the halo abundance, the halo mass function. Okay? Then you need to know if the clusters are clustered with each other. And we know that because we've just done the model for halo biasing. Then you need to know how the galaxies are distributed around the center of each cluster. We will call that, so for a cluster, we will call that the galaxies around a cluster. But for dark matter particles, it's the halo profile around the center of a halo, which so far we have not discussed. Okay? And then we need to know what is the number of galaxies per halo. Okay? So this is the only extra step that we have to add. Now, when they did this, they set up a model and they said, these are the ingredients, and now how will you write the two-point function? Or how will you write the PDF, the non-Gaussian PDF? So how will you write these things? And they wrote down formulae for how to do it, but in their case, they didn't know any of these things. So they were trying to see then from measurements how you can figure out these things. We are luckier, no? In the 50 years since, we now have models for a bunch of these things. So the only unknown for us is going to be the number of galaxies. So I've already described these two, then I'll describe this very briefly, and then we'll work this out. Okay. Okay. And so, for the model of the dark matter, we're using the fact always that structure is local, okay, and cold, and so we have late-time memory retaining, late-time field retains memory of initial conditions. So the only question is, we have the dark matter field is made up of halos, and the halos are made up of subclumps, okay, and so what we're going to do at the end, we're going to imagine that each of these subclumps holds a galaxy. Okay? That's going to be the model. So this will be a cluster, and then in the cluster there will be a big galaxy in the middle, and there will be other galaxies. And we're going to call them the central galaxy and the satellite galaxies, the other ones. Okay? So that's going to be the model, although the precise details of where these guys are is not going to matter, as you'll see. But if you want a physical model in your head, that's the thing we're trying to work out. Okay. Let me see if I can run this movie. So the reason for saying each of those subclumps is associated with a galaxy is because if we ask, where's the gas? So in a simulation, there's dark matter only. 30 years ago, those were the only simulations. Then they started to add gas. And they found basically the gas is where the dark matter is, as it should be. But there is a difference, which is that the gas can cool and radiate photons. And so it can fall further into the potential well than the dark matter can. So the dark matter is, once it has an orbit, it stays on the orbit. It's collisionless. There's no way to lose energy. Okay. And so this is the result of a simulation showing that the gas is where the dark matter is, but we're going to look at the 3D distribution just a little bit, okay? We'll zoom into one of these lumps. As we zoom in, we'll spin around. I don't know if you can see, maybe it's a little bit bright. Let me try. It's all these switches, or? Okay, maybe that is good enough, yeah? There's that side also. So let me go back. This will just zoom in to a few of these guys. And the thing I want you to notice is for each lump, there's a galaxy, but the galaxy inside tends to be a disk. Yeah, so the lumps are 3D, but sitting inside them, the gas has cooled and made a disk. So the simulations are pretty realistic. They're able to do this quite naturally. They didn't put by hand, right? This is just conservation of angular momentum and things like that is causing the disks. Okay. But importantly, the galaxies are forming inside the dark matter halos. The galaxies are not forming between the halos. Okay, so we're going to use that fact, right? That basically, if you know where the halos are, if you know where the subhalos are, that's where the galaxies are going to be. Okay, and the gas has shrunk a lot compared to the dark matter. So the dark matter halo is somewhere out here, the thing that's 200 times the background density. And the gas is just in the middle. Okay. Okay. So the assumptions that we're going to be making that are all pretty reasonable is the late-time field is a collection of halos. These halos are all 200 times the background density, but they have a range of masses. The more massive halos are more strongly clustered, right? They're more biased. So the bias factor increases with halo mass. And galaxies form in these halos. Okay. The model is, one of these circles inside circles kind of thing. Okay. Except that it shrinks, right? That's all. So this is the RT picture. We have the halo mass function from the kind of thing I described, right? Halo clustering. So this is showing the clustering of the dark matter, which is the green. Okay, so that's the dark matter correlation function. And then all these other curves are clustering where you sit on a halo and you count the mass around it. Okay, so this is the cross correlation function between the halo and the matter. Okay, and so you can see there are differences on these scales, but on these scales, they all have the same shape and just the amplitude is different. Okay, and so this is the linear bias that we discussed just at the end of last time. And the more massive halos are more biased than the less massive halos. Okay, so the more massive halos, 10 to the 14, are less than the 10 to the 12. Sorry, the more massive are more than the 10 to the 12. Okay, so this is the linear bias, and we'll talk about this very soon. Okay, so we've done the correlation function, right? What is the correlation function? We've done this stuff. And we've done the fact that we actually have a model for the bias, right? So we did that in the last lecture. And so that means that if we, okay, so the one point I didn't make is I said that the bias is related to this kind of conditional distribution. Okay? But this kind of conditional distribution, I said you can make a Taylor series. But the Taylor series is basically something where if we had E minus delta C, now we do delta C minus some delta 0. Okay? So that's a little bit like saying the large-scale environment is just changing this value. Yeah? You're doing delta C minus the large-scale value. And so that's a little bit like saying the way you should calculate bias is don't worry about this. You just take derivatives with respect to delta C. Yeah? And that will give you everything anyway. You can think of it that way, or you can think of it as if you're taking derivative with respect to delta C, that's like a derivative with respect to the growth factor, because environment is an effective cosmology, and so you're taking derivative with respect to that growth factor. Mm-hmm. Either way, it means that if you have a model for the halo mass function, you have for free a model for the bias. No free parameters. Okay? And so this is that test. These are for standard CDM, open, lambda. Let's look at the top two. Okay? The top two is the halo mass function shown in this funny units that we said was the convenient way to show. That if you show in these funny units, then most of the dependence on cosmology should be taken away. Okay? And the symbols are outputs from different times in each cosmology. So most of the redshift dependence has been taken away. And so the fact that the symbols sit on the same curve is telling you that the time dependence of delta C has been accounted for. And the fact that this curve is the same as this curve is saying that by working with sigma, most of the power spectrum dependence has been taken away. And the fact that the symbols sit on the curves is telling you that working in this variable is the right thing to do. And so, okay, so the main thing is to say we have a pretty good model for the halo mass function. And coming with this model for the halo mass function is the bias factor. And so this axis here is showing you the bias factor. This is, again, in some scaled units, but the basic idea is halo bias is here and halo mass is here. These are high masses, these are low masses, just like big nu is high mass, small nu is low mass. And again, you know, if you work in these funny units, then you get a model for the bias that even when you put different redshifts, you know, you can put them all on the same kind of curve. Right? So this is just to show you that the technology that we've developed to do the halo mass function gives halo bias for free with good accuracy. Okay. So 2 of the ingredients of the Neyman-Scott program are done. Okay. So this is just making that same case, the slide that we saw before, right? So the third ingredient we need are the halo profiles. So this is the only one that we haven't done in this course, right? And so the halo profiles, again, for a wide range of models. This is standard CDM, this is lambda CDM, and then these are a bunch of power law power spectra, simulations run with power law power spectra. You then measure the halo density profile, so the number of particles as a function of distance from the center. And they're all pretty well fit by this functional form. The functional form has two free parameters, a density scale and a scale on which the slope of the density profile is changing. So when at very small scales, this number is small compared to this, you can throw this away. And so the profile is 1 over r. And at very large scales, then you can't throw this one away anymore. But this one is big compared to 1, so it's 1 over r cubed. Okay, so it's a profile that is 1 over r becoming steeper to 1 over r cubed. And this functional form, if you keep those two free, you can fit basically all halo profiles from all simulations. There's some interest in doing slightly different fitting formulae these days, but the basic idea is this, that there's a formula that can describe it. Unfortunately, there's no good derivation of this formula. So it's just an empirical thing that people can that people use. Yeah. The crude derivation or physical reason for why it works is the following. If a density profile is r to the minus 3, then if you calculate the mass is dr r squared rho r. And if rho r is 1 over r cubed, then dr r squared over r cubed is diverging as the log. So the mass is not well defined. Okay? So what does diverging as a log mean? So supposing we ran a simulation where there was, the matter could collapse and nothing else falls afterwards. So it really is an isolated object. That density profile becomes r to the minus 4. Okay? So r to the minus 3 is saying you still have accretion, all objects are still accreting, and so they're not isolated objects, and that's why it's not falling as steeply as r to the minus 4. We're still in a hierarchical universe, cluster is still ongoing. Okay? So that's the heuristic argument for r to the minus 3. And the r to the minus 1 is, so because structure is always, you're always adding to the mass, you can ask, does the mass that you add, is it sitting at the outside like a shell of an onion, or does it fall into the middle? And you saw before that there were lots of subclumps. So you can ask, what happens with these subclumps? So what happens with the subclumps is they fall towards the center, and as they fall towards the center, then their mass gets stripped from them, because a crude statement is, if their density is the same as the density of the place where they are, then they will lose that mass to the parent halo. They won't keep their own mass. Okay? So that means, and this is not exactly true, okay? There are recent papers studying how good this is, but it's a good rule of thumb, but it's not perfect. So that means that a subclump, as it falls into the center, it's losing mass because the density profile of the central guy is bigger in the middle. So it's losing mass. If it passes closer to the center, it loses more mass. Losing mass means mass was added to the center. Okay? So if you add mass to the center, you will change the density profile in the central regions. And so now you can say, if you start depositing lots of mass in the center, then if that density profile is flattening out in the center, then the rate of change of the density profile is different. Rate of change with distance from the center is different. So it becomes less efficient at stripping stuff, depending on how close it got or not. So there's a kind of trade-off between how much stuff can arrive to get stripped to change the profile, And if the profile gets too steep, then not enough stuff will get stripped. And so there's a trade-off, and r to the -1 is this in-between, between the stripping and the steepening. Okay? And so again, it's a heuristic, hand-wavy way of getting the profile. There's not a first principles thing of saying what was the initial phase space, and that phase space ended up producing this density profile. That doesn't exist. Okay. For our purposes, it doesn't matter. For our purposes, it's just that there's some shape that you can use that describes the halo profiles. Okay. So let me skip this. So let's try to put this together. So the Neyman-Scott model is this. We have halos which are a bunch of different masses. But for us, they're all 200 times the background. And so big mass has big radius, small mass has small radius. Okay? And although I've drawn these like little explosions, just think of these as different dark matter particles. And now we can do, suppose I want to model the two-point correlation function. So the two-point correlation function is a statement about number of pairs. And so we can say, if I fix a separation, I want to know the correlation function at 10 megaparsecs. Then I will always have two types of pairs. Either both members of the pair are in the same halo, or one is in one halo and another is in a second halo. So that means that my number of pairs, 1 plus psi is the number of pairs. There are two types, pairs in the same halo plus pairs in separate halos. Okay? And we will call this the one halo term, and we will call this the two halo term. Okay. So this is just a very vanilla statement, right? It's obviously true. But where the trick is going to come, or where the meat of the model is in saying that this thing that is obviously true for the statistics, we're going to now say is true for the physics. Meaning that anytime we have to do something with this kind of pair, we're going to say that's nonlinear physics virial theorem. And anytime we have to do something with this kind of pairs, we're going to say that's linear theory. If you want some linear perturbation theory, but just linear theory, the simplest thing. Okay? And what I mean by that will become clear as we keep going. But so for now, just have in the back of your head, the split in statistics means a split in physics as well. And we will use this. Okay. So 1 plus psi is 1 plus 1 halo plus 1 plus 2 halo. Okay? So if I'm interested just in psi, because that's what we usually look at, I can subtract the 1 either from this term or from this term. And so we will usually subtract it from this term. Okay? And that's because of the following. Suppose that the halo centers were thrown down at random, so they were not clustered. But although the centers are not clustered, inside a halo there is a density profile. So the particles inside a halo are clustered. Okay? So then we will say, in such a model, because the particles inside a halo are clustered, we will certainly have this kind of pair. And if the halo centers are not clustered, then although we will have pairs that are particle in one halo and particle in another halo, they will be like random pairs. So there will be pairs, but this term will be 0. There will be no excess pairs because of this. Okay? And so we'll usually subtract the 1 from this term. Okay. So that's why I'm writing it this way. We'll write the correlation function is 1 plus the correlation of one halo. So this is the number of one halo pairs, and that's the two halo correlation function. Okay. So let's do this term first, the one halo term. So the one halo term, the pairs have to all be in the same halo. Okay? And so the halos have a range of masses. Each halo will give me m squared pairs, the total number of pairs, but not all of them will have the right separation. So I have to take a fraction of m squared, which are the right separation, the separation r that I'm interested in. Okay? And so what does that mean? Well, it means that I should go to each particle in the halo and I should ask how many others are within distance r from here. And I should do it for all of them. And so that's like doing delta at position r, and I want to know, or delta at position x, and I want to know what is delta at position x plus r. And I want to do this for all my positions x in the halo. So it means I'm doing like a convolution, yeah, of the density profile with itself, right? Because both particles are somewhere in the halo. Okay? And so this term is the convolution of two of those profiles of fixed mass. Okay? And so each profile will give me a convolution of two profiles of fixed mass for the pair counts. I want to evaluate that at r. So I will get m squared times this fraction at r. And now I have this many halos of this mass. And so I have to integrate over the halo mass function. Okay, so this is called the one halo term. These are all the pairs that are in the same halo, and all the pairs that have some separation r. So halos have a range of masses. Typically, the biggest mass is 10 to the 15 solar masses or something. So the virial radius is a few megaparsecs, 2 megaparsecs. And so beyond 4 megaparsecs, there are no pairs like this. Beyond 4 megaparsecs, all the pairs will be two halo pairs, not one halo. Yeah? So that means on small separations, we expect all the pairs to be given by the one halo term. And on big separations, all the pairs will be the two halo term.
So the fact that there are no pairs within a certain halo after the radius is encoded within the E, within the xi.
This term here.
DM term?
Yeah. Okay. So this will be something, suppose this was, suppose we thought the profile was a top hat. We know that it's not. And suppose we thought it was the top hat. Then if you convolve a top hat with a top hat, you'll get something that goes to 0 at 2 times the radius of the top hat. Okay? And how it goes to 0 will depend on whether it was a top hat or whether it was NFW or whatever. Okay? And so that information is encoded in this shape. Okay. So what else do we have? And so this is, this thing is dimensionless, and this thing, so this is really the dimensionless quantity. Okay, so I need to normalize by the density squared. One way to think of it is if you put this density squared term here, so the units are density squared. That density squared is coming because you convolve two profiles. Yeah, and we're getting a density term from here, and from here we're getting we'll get one of the density terms and the other is going to go away because we weight by mass, and we're integrating over a volume when we do the convolution. Okay, but the dimensions are in fact all fine. Okay, so that's the one halo term. So importantly, for this term, you need to know the halo mass function, but you don't care about halo bias. Okay? And that's because the term is one halo at a time. So you don't care about pairs of halos. For the two halo term, so now we want to do this term. The two halo term, what's going on? So I pick a separation, 20 megaparsecs. It's a lot bigger than the size of one halo. So now I have to take a particle in this halo, and now I have to find everything that is 20 megaparsecs away in the other halo. But the other halo, there's some probability that it is closer and some probability that it's further away. So the center of the halo can be some separation like this. And then this particle could be anywhere inside this halo, and the particle here could be anywhere inside here. And that combination of distance from center, and separation of centers, any of those combinations can work. So now I have a convolution of three things. Okay? Those three things are the density profile, and the correlation function of the halos. Okay? And so that's what I've tried to write here. Oops. This is, my particle could be anywhere inside one halo, anywhere inside the second halo, and now the halos have to have the right separation, and the particles have to have the halo separations and the particle positions in each halo have to work out to give me R. So this is the result of a triple convolution. Okay? And this is the term we're expecting will dominate on large scales because there are no one halo pairs with large separations. And we have a model for this guy, right? Our model for this guy was that at very large separations, at least the halo-halo clustering is going to be a bias squared times the dark matter clustering. And now if our halos have separate masses, there will be B1, B2, psi matter. Okay, so that's the B1, B2. And if the separation is very large compared to the halos, then it doesn't matter where I am in this halo, it doesn't matter where I am in this halo. The center has to be exactly right or I won't get it. And so it's almost like you can pretend the halos are point masses, but with a lot of, all M is concentrated at the center. Okay? So that's an approximation. That's a convenient one when we do this in real space. Okay? And so that's what's written here, right? That although the exact expression is this, where this is some complicated triple convolution, this one is well approximated by saying we put B1, B2, psi of the dark matter, or psi of linear theory. Yeah? Because linear theory should be fine on large scales. Okay? But if I put B1 here, B2 here, and psi of linear theory doesn't depend on M1 and M2. So that comes in front, comes out of the two integrals. And the two integrals are otherwise identical, dm, m, nm, bm. And so I just have the same integral squared. Yeah? So these two separate integrals are the same integral with m1 or with m2. And so that's our expression for the two halo term. Okay. So that's the halo model of the dark matter. Okay. Let's do this for the power spectrum. If we do this for the power spectrum, then it's a little bit easier. So the one halo term is about as complicated, right? We have to do some integral over the halo mass function. We got m squared pairs. And the convolution of the two profiles is now the product of the Fourier transform of each profile. Okay? So this one is simple, because now I just need one Fourier transform to know the shape, and then I just square it, that's all. The two halo term is where Fourier space really helps you. And it really helps you because you had to do this triple convolution. Okay? But the triple convolution means that in Fourier space, you will just have a product of the three profiles, the profile of halo 1, the profile of halo 2, and the profile of the separation between them, which is the power spectrum of the separation between them, instead of the correlation function. Okay? And so we will have B of halo 1, B of halo 2, power spectrum of the dark matter. And so that means we have the two integrals, dm, nm, bm, m, and before, And now we know that we'll get the halo profile, halo 1, halo profile of halo 2. So we're going to get this thing squared and the power spectrum of the dark matter. And our approximation when we did the real space thing, we had the same this stuff. We had no U. We didn't have the equivalent of the profile in here because we said we're going to approximate them as delta functions. Right? We said the halos are small compared to the separations between them, so all the mass is contributed always. And so that corresponds to setting this U equal to 1. Because the Fourier transform of the delta function is the 1. Yeah? Okay? So in that respect, Fourier space is better because it's letting you account for the convolution. Okay. All right. It's also better because, if we were doing the linear theory stuff or we were doing Zeldovich to give us the large-scale separation, we know that power spectrum is wrong at small scales. Okay? And what this is doing is it's saying, if I take that thing, the power spectrum from linear theory, and now I multiply by some function of k, all profiles, they're all equal to 1 at small k, and then they're all decreasing. So always think of these as a Gaussian. E minus k squared r virial squared. Okay? So these are all dropping at big K, and so they're killing the wrong prediction of Zeldovich at big K. So they're killing the wrong prediction of linear theory, and they're replacing them with the 2 halo term. With the 1 halo term, which has the nonlinear physics. Yeah, so that's what the halo model is doing for you. Okay? Wonder what's going on. Yeah. Sorry?
When we are having one halo term, there we are not having the correlation.
Then we don't have the correlation, right? So in this term, there's no correlation because by definition, all the pairs are in 1 halo. So we don't care whether there's a second halo there or not because the definition is there in 1 halo. Yeah? And so maybe another way to say it is this.
Within 1 halo, but there are 2 of them, 2 particles. So they may have some correlation.
They can have some correlation, but that's what you mean by the density profile. Yeah? So the density profile is the correlation. It's really the convolution of the density profile with itself is the correlation. Okay? So by using the density profile, you have put in some correlation, and that's all you need to put in for the 1 halo. For the 2 halo, you need, in addition, the fact that the halos could be themselves clustered. But that's all.
What would m by rho into a density profile give you physically? Would it be a number count?
So you should think that I've tried to make it so that the normalization in Fourier space is easy. So in real space, you would not say m times rho. You would say rho is equal to m, which is the I should say differently. The way to think of the profile is to think of it as m times a shape, times an r-dependent thing. The reason for saying m times something is because the integral of rho, drr squared, that should be m. So it's like you want the...
itself should be dimensionless?
So the u is dimensionless, and the dimensions are coming here. Okay. That's the idea.
I'll talk to you later about how I break this up.
Okay.
One halo term.
I mean, if you want, you should think of m, nm, dm. If I divide by, it's a mass density because it's a number density.
Right.
So this is a mass density. If I divide by rho, that's also a mass density. So that piece is dimensionless. Then I have an m, a u divided by rho. So the m divided by rho is a mass volume, and power spectrum has units of volume. Yeah. So that's the way the dimensions work out. That's why we usually work not with power spectrum, but with k cubed p of k to kill the dimensions of volume. Okay. So that's the halo model description of the dark matter. Our goal was to do it for different tracers, so now let's do the halo model description of galaxies. And so I've used the same picture as before, but now I've put colors for the galaxies to represent different galaxy types. Okay? Again, we will split it up. We will split it up into galaxies that are in the same halo or galaxies that are in separate halos. Okay, so that I can still do. And I could write everything the same as before, but I'm going to be slightly more careful in the following sense. I'm going to distinguish between the galaxy that's in the middle of the halo and all the others, because the physics for the guy in the middle might be a little different. Okay? And right now, for the statistics, it doesn't matter. But just because very soon it is going to matter, I'm setting it up this way. And so now I can think of the correlation function of, so the contribution from the single halo. There's some total number of pairs from the single halo, right? Distinct pairs, if there's nt particles, nt minus 1, okay? These number of pairs are divided up into I cannot have a central pair because there's one central galaxy, but I can have central satellite and satellite. Okay, where satellite means not at the center. Okay, it doesn't mean in another halo. It means in this halo, just not at the center. Okay? And so I will have this many ns n minus 1 non-central pairs. I will have maybe the way to think of this is I want distinct pairs. So distinct pairs would be n minus 1 over 2. So this over 2, this over 2, and then central is distinct from satellite, so I didn't need to divide this by 2. No? So that's why this has a 2 and the others don't. Yeah. And then these guys are saying, what's the fraction that have separation r? Just like before. Okay? And we will do this split for each halo mass. No? So in principle, this is at fixed halo mass, and so on. Okay? So this term just looks more complicated, but the logic is very similar.
Any limit on the halo mass, no?
Okay, I'm not putting any limit on the halo mass. So what I'm going to do, though, is I'm going to have to integrate over halo masses, right? Because also when we were doing the dark matter, we do an integral over halo masses. And when we do that integral, we integrate over all masses. Okay? So let me now see what we have to do with galaxies. Because you're right to think that a very low mass halo will not have a galaxy. And so how do I do this? So we'll do that. Okay. So the one halo term, we would still write as nm dm, the number of pairs, the thing that for dark matter is m squared, okay? And then we would have the correlation function of the convolution of the halo profile. So before we had this guy as m squared, okay? Now we have to say, well, maybe it's not m squared, maybe it's different from m squared, because maybe, as you say, a very low mass halo has 0 galaxies. If it has 0 galaxies, it has 0 pairs. And so I should put this one 0. And so that way I will put a cut on this integral, no? Because so physically we believe there will be something with 0 here at sufficiently low masses, and then it will rise up. And then maybe at large enough masses, it will be proportional to halo mass. I don't know, right? But that is the kind of thing that you might expect, that a very massive halo will have more galaxies than a very low mass halo, okay? But that's the one thing we don't know, okay? So we don't know what this thing is for an arbitrary galaxy population. So what I'm going to do is I'm going to set up the formalism. Then I'm going to, in a simulation where I can just measure this thing, I'm going to put the input from the simulation, and I'm going to check that the formalism correctly described the clustering of the galaxies. If it does, then I'll say, okay, I have a language that works. Then when I go to data, I observed a correlation function, I will, the number, what I will extract from the data is this function. How many galaxies per halo? Okay, so that's where we're headed. So the first thing is we're doing pair counts. So there are two kinds of things, two pieces of information we need about a halo, about the number of galaxies in a halo. So there is some probability that a halo of mass m contains n galaxies. Okay, so there is some distribution P of n given m, n galaxies. Okay. This distribution has a mean. That mean is what I'm calling G1. This distribution has a variance. That is what I'm calling G2. Okay. So this is telling you if I'm doing pair counts, then I only need the second moment of that distribution. If I was going to do a 3-point function, I would need the third moment of this distribution, and so on. Okay? And now you know I can, so this is the number of pairs, and now I can separate the pairs if I want. So this is the thing that would be like the nt minus 1 on the previous slide here. That's the thing that we're calling G squared, G2. And I can separate it up into central and satellite if I want. Okay. And so there's the G2, there's the G1, right? Except for this, everything is like for the dark matter. Okay, so the setup is the same. 1 halo, 2 halo term. Again, we put the game and we replace m with the mean number of galaxies. We place the rho bar, which was before the number density of matter. Now it's the number density of galaxies. Okay.
Just change your counting.
That's all.
From the number of halo pairs to the
number of galaxy pairs. Okay. So logic is the same. Setup is all the same. Importantly, the mass function is still the same as for the dark matter. And the bias factor is still the same as for the dark matter. And so the only difference between dark matter and galaxies is this weighting. For dark matter, this is proportional to m, and this is proportional to m squared. And so the reason a galaxy survey looks different from the dark matter is because those functions are not m and m squared. That's all. Okay. And so in that sense, you can just think of this as, I say you can think of it as a weight that you're applying to the halo distribution. Okay. All right, then we've done central satellite models. Okay, the last trick, or the last thing we do for convenience is, so if I wanted to split up my number of pairs into centrals and satellites, then I have to think, how do I do that? Okay, so there'll be one central. But what about the number of satellites? Do I need a free parameter to describe also the number of satellites when I do the split? And the trick that works quite well is to say that the number of satellites is a Poisson distribution with mean given by the number of galaxies minus 1. The Poisson distribution has no other free parameters, and so there are no new free parameters. So in fact, the only information that I need is this, the mean. And we'll get all the rest by saying central is central plus Poisson satellites. Okay, so that's reducing the number of things you need to know. And this works quite well. So the difference from dark matter is this is m squared and this is m. But now I could say, what happens if I do an X-ray cluster or X-ray luminosity? Well, then I just figure out, I put my virial theorem arguments that convert for a halo of mass m, what is the v squared to a temperature. So now I know X-ray temperature, and I can put the weight, that is the X-ray temperature, as a function of halo mass. Okay, and so you can do the same for the SC signal. What is the pressure as a function of halo mass? And so this allows you to do any weight that you want as a function of halo mass. And that means that all large-scale structure observables are just weights as a function of halo mass, and this is letting you calculate anything. We're doing it for galaxies, but you could put anything. Okay. All right, once again, convolutions in real space are products in k-space, and so that means that in two-point function, there was some gain in going to k-space, but 3-point, 4-point, 5-point, where you're doing these multiple convolutions and they're just products, you gain hugely by working in Fourier space. Okay, much simpler. Okay, if you want not 2-point but 3-point or 4-point, then you need to know the nth moment of the galaxy distribution for a function of halo mass. Okay, so here's measurements and simulations of the first moment, number of galaxies as a function of halo mass. It is, as you were expecting, at small enough masses, there are 0 galaxies. You have to be a massive enough halo to have 1 galaxy. And then as the halo mass is bigger, you might have, on average, more than 1 galaxy. Okay, so that's something measured in simulations. So in the simulations, they also divided up red galaxies from blue galaxies. They have different number of galaxies as a function of halo mass. Okay, so the red ones are this curve, and the blue ones are lower, but this way. So you can see from this that the blue galaxies, they sit in the low mass halos, and there are few of them in the high mass halos. So you expect, because the high mass halos are strongly clustered, you expect the blue galaxies are not strongly clustered. The red galaxies should be more strongly clustered. What's that? They have some complicated scheme where they go through the whole merger history of the stuff. So for this, it's not important how they did it. It's just that the red galaxies are a different set of particles in the halo than the blue. And so, but there's a full semi-analytic galaxy formation thing that has gone into doing this. Okay? And so there's a whole field, right, of people trying to make predictions for how you turn the gas of a halo into galaxies. Okay? So this is the result of one of them. And I'm just doing it to illustrate how the formalism works. Okay?
So this red and blue is according to luminosity, no?
No, so the models, they do, they give the luminosity in many different bands. Okay, so typically in 5 bands. And so then they can define red and blue just from that to mimic some data.
That means typically how much energy they are emitting.
It means typically how, yes, but it typically means how old are the stars.
Okay.
Yeah, so old stars are red, young stars are blue, because the young stars are putting out a lot of energy.
Yeah.
Yeah? So that's basically how it's going. And so that also you can see will make some sense, because the massive halos are the ones with the red galaxies. There are not as many blue as red galaxies when the halo mass is high. When the halo mass is low, it's vice versa. Okay? So that's because the massive halos, they started pulling their matter together earlier, because they have to make a big mass by today. And so the galaxies that formed in them, they started forming their stars long ago, because they're the places where the collapse happened first. And so the stars are all old now, so now it's red. Yeah, so physically, that's why there's more red than blue in the massive halos. Yeah. And we know that because we looked at the formations of objects, and so we know that the big guy will have got more of its pieces. You know, the big guy was more likely to have had the subhalos that crossed the barrier at higher redshift than low. Okay, but again, that's not so important here. All that matters is that there's some curve that we can use. Okay, there's some curve that we can use from here and predict what should be the clustering of the red and what should be the clustering of the blue. And then we can compare with the direct measurement of the clustering of the red and the clustering of the blue and see if this works. Yeah? And so this is the correlation function that is measured of the red and of the blue. And the lines are the theory prediction for the red and for the blue. The red have a slightly bigger amplitude than the blue on small scales. That's the bias factor because the red sit in the more massive halos. And then the amplitude of the red is very high compared to the blue, because the blue, there are mainly one galaxy per halo. And where there are more than one galaxy per halo is only in the very massive halos, which are quite rare. And so there are very few close pairs of galaxies. Whereas the red, they populate the massive halos, and so there's lots of close pairs in the massive halos. Okay. All right, but an equally nice thing here is not just that you could predict the clustering of the blue and the clustering of the red, but the black circles here are the dark matter in the simulation, the clustering of the dark matter in the simulation. And the small dots here, that's the prediction for the dark matter when you replace those weights, instead of for the red or for the blue, with m squared. And so this really is a framework that describes all the different tracers with the same framework. You just change that weight. That's the only thing you have to change. Okay? The mass function is the same, the bias factor is the same. Okay. So that is for the clustering of galaxies. Another observable is weak lensing. So the weak lensing is doing, the light traveled from the source. So the light traveled from a source to us. As it's traveling, it's getting bent and distorted. And so if the source is really spherical, it arrives to us as some strange shape. Then we can measure the clustering of how strangely shaped these are to infer what is the dark matter near here. And yeah.
Let's say you have a source somewhere and you're observing it somewhere. Won't the final path of light be a sum of all the changes that you get from all
Correct.
the dark matter along the
Correct.
side?
Yes. Yeah.
So how do you decouple all that to really get a three-dimensional image?
Right. So nowadays, they can make a so let's say in an ideal world, what would you do? In an ideal world, you would know the redshifts of all the background things. So then you would just do the same measurement, but in shells. You would take sources very far away, sources closer to us, and then subtract the two. Okay? So this is called tomography, and you separate out the individual redshift contributions. Okay? So let's say you do that. So then you will have the dark matter mass that has contributed to the signal. Okay? But currently, at least, it's tough to do it just with the shapes. So currently what happens is you sit on a galaxy here in the foreground, and you measure the bending or the warped of a background galaxy, the image that is distorted. So you're not doing distorted image with distorted image. You're doing galaxy with distorted image. Galaxy here with distorted image here. Yeah? So this thing is called galaxy lensing, because you sat on a galaxy and measured the lensing of another galaxy, okay, by the intervening matter. Okay.
So that's close by, so that's less matter, so you can estimate it better.
No, so what's going on is, so it's really saying that the shapes can be distorted, okay, and this distortion and this distortion are supposed to be correlated. Okay, so because the signal is not that this is elliptical. The signal is that this ellipticity is correlated with this ellipticity. They're not just totally random. But if you're measuring the ellipticity and the signal is very weak, okay, you need a very big sample to measure it. But if I have a galaxy sitting here, then I know that these ellipticities of the other galaxies are going to go around. Okay? And so that means all these are going to be oriented tangentially. So I can stack that to get a much better signal. Okay? And so sitting on a galaxy and measuring the sheared image around a galaxy is a higher signal to noise measurement than ellipticity with ellipticity, which is not necessarily sitting around this guy. It might be rotating around that guy. Okay, and so that's the higher signal to noise measurement that is currently done. The cost is that this measurement is telling you about dark matter and dark matter. Galaxy with dark matter is now telling you galaxy and dark matter, not dark matter and dark matter. So you've lost some of the beauty of doing lensing, which is now you need to know galaxy bias. Okay, but you're getting much higher signal to noise. So let's look quickly at how we measure that. For galaxy lensing, yeah.
This is to take tomography of dark matter. So that is in simulation.
Also in data.
How do you do that in data? Through lensing?
Yeah, so in an ideal world, we would have spectra. So we could just separate the background galaxies into thin shells and redshift. In reality, that's way too expensive, so we don't do that. But we can take shells in photometric redshift, which we estimate the redshift based on the observed colors. And then you can do this. So they're slightly thicker shells, but better than nothing.
So that is how we reconstruct the original.
Yeah. Yeah.
But there will be so many errors in this.
Yeah, there will be errors, but so one way of saying it is, so you won't know something very precisely. But okay, before you knew nothing, right? so you go a step at a time, right?
Like the amount of distortion due to lensing.
Yeah.
So much that it doesn't matter that at every.
So the distortions are pretty weak, right? So that's why you need a really huge survey to do it. That's why we have billion galaxy surveys, because it's hard to do, right? And so it's one of those things, no? Because we have no idea what is dark matter, we have no idea what is dark energy. People think these are important problems to try to figure out, and so they're willing to spend the money to do it. But
The number of galaxy we see in the simulation are much lesser than the galaxy that we are actually seeing, because there are more number of images that due to the lensing.
Well, so in a real survey, there are issues like your telescope will only see the bright enough galaxies and things like that. So in a simulation, you have a bunch of that under more control. So you can check things better, but you'll always turn your simulation.
We are getting many more images of one single galaxy.
That will only happen if the, suppose most of the mass is sitting here that is doing the lensing, and these things are supposed to be galaxies in the back, and their light was coming to us, and as they were coming to us, the light got distorted. So the light got distorted, and because they are far from here, they just got distorted. But if there was a galaxy that was almost exactly behind this, that's the one for which there could be two different paths, and that would be the strong lensing. So this is called weak lensing, because there were not multiple images, they were just changed in shape. Yeah? Okay. So how do we model the weak lensing signal when it is galaxy lensing? Okay? Because once it is lensing, then that's like the matter-matter correlation function, and we've already modeled that, right? I showed you we can do that. So now we need to know what happens when one of the tracers is the matter and from the lensing, and the other is a galaxy. So we come here and we say, well, we are doing the one halo term, but now the two members of the pair, one of them is matter, so I put m times u, and the other is galaxy. And so that's a galaxy times the profile of the galaxies. Okay, that's all you do. Here, in the two halo term, one term is going to be the matter, and the other integral is going to be the galaxy. That's it. Okay? This term is actually simpler than it looks. On large scales, this factor is u. This factor is 1. This factor is 1. And so this is just some integral over the bias. The dark matter, all the matter that contributes, so the integral of all of this is actually 1. because the matter is not biased compared to itself. Okay, so this integral is going to be 1, and this integral is going to be the mean bias of the galaxies, some B galaxy. And so this term is really going to be B galaxy times P dark matter. And that was the crude thing that I had written last time, no? Delta halo, delta 0. When I was introducing bias, I put one factor of bias. That's the weak lensing signal. Yeah, so that's this guy. And this one, you will have a measure of the profile, except almost everyone will put in the galaxies are distributed also like the dark matter, so they will put the same NFW profile here as here. Here I've put a little g to say maybe the galaxy distribution around the center of the halo is not NFW. Okay, but almost all analyses make it equal to NFW. But in principle, it need not be. Okay. But so that's the model of the weak lensing signal. Okay. And now we just need redshift space distortions, and we're done. Okay. So this is where we care about the physics being different for the one halo than the two halo term. Okay. Or let me skip this. And so we're going to think of the velocity that is making the redshift space distortion as the sum of two terms. One term is a particle's velocity is because it is moving compared to the center of its halo, so we call that the virial. And then the halo is moving. So that's the halo plus the virial motion, the motion with respect to the center of mass. And so because we're going to say linear physics and virial physics, this one is given by virial theorem, and this one is given by linear theory. Yeah? For virial theorem, we know there's a relation between the typical speed and the mass, because all the halos are the same density. So the more massive halos are hotter. And for a Gaussian velocity, well, we just do the statistics of Gaussian field, and it's linear theory. If I smooth, it's something I just can compute from the matter power spectrum. Okay? We know that the matter power spectrum has some shape, P of k. The velocities, because velocity is 1 power of k different from density, the power spectrum of the velocities is pk over k squared.
So that will be your variance when you pick.
That's right. That will be the variance for the velocity. Even nicer, that means this, for any particle, is drawn from a Gaussian distribution with variance p of k over k squared integrated over all k. This will be a Gaussian because it's a Maxwell-Boltzmann distribution of the virialized guy. So it's a Gaussian with variance given by v squared is m to the 2/3. So this one will depend on m, and this one will not depend on m, not very much. But the sum of two Gaussians is Gaussian, or convolution will be Gaussian. So this will be a Gaussian with a variance that depends on m because this one depends on m. Okay? So convolution of two Gaussians with variance, the virial one plus the linear theory one. Okay? This is just a check in simulations that the variance of the virial theory really scales like we expect, and the variance of the linear theory velocities really is essentially constant. If you're interested, I can get into the slight trends with mass, but importantly, there's 4 orders of magnitude here, and this is changing by a tiny amount, whereas here it's 4 orders of magnitude, and it's really scaling much more strongly. Yeah, so it's a pretty good approximation. Though nowadays, people are interested in this slight curvature. But for this discussion, it's just important that this is flat and that is not, right? We can calculate both. That's the important thing. Okay. And so if I wanted the 1-point distribution of velocities in the halo, so the thing, it should be Maxwell-Boltzmann. What is it now? Yeah? What is the nonlinear distribution of velocities? And so now it would be Gaussian, so like Maxwell-Boltzmann, at fixed mass, but now I have to integrate over the different masses. Each halo gives me m particles, and I integrate this, and so I will get a weighted sum of Gaussians of different widths. Okay? So this is just some algebra to show you So one is doing the Fourier transform because I have Gaussians of different widths. This was itself a convolution. And so this convolution will be E minus t squared virial squared, E minus t squared linear squared. This doesn't depend on mass, this does. Okay? And then it turns out you can do this analytically to see what it will look like, but even for a general CDM spectrum, you just do numerically. And the idea is going to be that you have broad Gaussian for massive halos, narrow Gaussian for low mass halos. You have many more low mass halos than massive, and so you will get a sum that looks like very narrow Gaussian and very broad Gaussian. So when you add the whole thing up, you will get something that has extended tails compared to a Gaussian, because massive halos and low mass halos. Okay? That's for one point. Now we need to do redshift space distortions. We need 2 points, no? Pairwise velocities. And when we do the pairwise velocities, remember, there's going to, again, we're going to think of the linear contribution and the nonlinear contribution. Okay? And so when we want to write this, then we'll say, well, 1 halo and 2 halo term, here we have to put the virial motions, here we have to put the linear theory motions. Okay? And so what happens? When we put the virial motions, then we will say, well, the distribution, the profile will be the real space profile convolved with the mistake you make because of the virial velocity. And because it's convolution, it's simple multiplication in Fourier. Okay? So you have to multiply by Fourier of a Gaussian. That should be E minus k squared sigma squared virial. And now I just want the component that is along the line of sight. And so that's the mu. Okay? And so that means that, that when I put in the redshift space profile, I should put in this rather than just this. Okay. And it's a 1 halo term, and so all the densities are wrong by the same Zeldovich motion. So this is the 1 plus f mu squared that was coming for the Zeldovich. So redshift space is arriving here and in the shape of the profile. For the 2 halo term, we're going to have, we'll have the same bias factor as before, but the 1 plus f mu squared is now a bias factor plus f mu squared. Okay, that's all that happens. Okay, and so here's the bias plus f mu squared. There's the G1, and there's the U, which has been distorted by the virial motions as well, right? And so this is the fingers of God. This guy is the linear theory. This is the bias plus linear, and this one has the fingers of God. Okay, so everything has been put in, and that's the halo model description of the redshift space power spectrum. Okay, so that's it. So now you have on these slides, you have the way to model all the nonlinear observables currently in use in large-scale structure. So I'm late. Can I go 10 minutes? Yeah? Yeah. So, so I want to show you the result of doing this in practice, okay? Because it turns out that you can do one nicer thing, not just large-scale structure from this. So I want to show you that. Okay, so at the end of the day, all these methods, they're trying to, the unknown, the unknown is always this G1 or G2. Okay, so at the end of the day, that's the information that you're getting out from a survey. And so there are different ways that people have tried to get it out. These have funny names. HOD stands for Halo Occupation Distribution. So that one is really trying to get out the G1, the G2, as I described. Okay. So another is called a conditional luminosity function. The conditional luminosity function is saying, typically what's going to happen is you're going to select galaxies not by their color, but by their luminosity. And so what we're going to try to model is we're going to try to say the distribution of luminosities in a halo may be different if it's a massive halo than if it's a low mass halo. And so they're going to try to parameterize that distribution with some free parameters, and then they want to work out how those parameters depend on halo mass, and they will try to fit. So it's a little more complicated. It's not as simple as I've laid out here. Okay? And so I'm just giving you the word to know that there's more than one way to do what we're doing. I'm going to go through this way because I think it shows most clearly how things work. Okay? The final is called sub-halo abundance matching. And if I have time, I will talk more about this guy. So let me just develop this guy so you can see what's going on. And so we're using the halo counts to constrain number of galaxies per halo. Okay? And we've already done the central plus Poisson satellites. Okay? So on this slide, I'm just telling you how you should put in the things for the redshift space distortions if you have centrals and satellites. Because now if you have a central, that guy doesn't have virial motions because that guy is sitting at the center. Only the satellites have virial motions with respect to that. And so you have to be you have to put a little carefully which guy gets the virial motions and which doesn't. And because it's sitting at the center, it is not following an NFW profile. It's always sitting at the center. So the central guy does not come with a U. The satellite guys come with a U. The central guy does not come with virial motions. The satellite guys do. So that's the stuff that I've written here. So that's all technical details. Okay? So you can look at this for reference later. Okay? It's just to show you that all that stuff can be just put in without a problem. So here's the data. Okay? So on this axis are measurements of clustering of galaxies, of luminous galaxies and faint galaxies. So the clustering depends on luminosity. Okay? It's actually not as strong as they've shown here. They've actually offset them a little bit, but the clustering depends on luminosity. Okay? A technical note is when we were discussing redshift space distortions yesterday, then I said, that full redshift space distortion thing, you can do the projection. You can integrate along the line of sight to measure only the one that is perpendicular to the line of sight, because that guy is independent of peculiar velocities. You remember when I said that? Yeah? There was the nice butterfly diagram, and I said, okay, we can just take integrals at fixed separation down there. That's that measurement. Okay? So this guy has no redshift space distortion problem. Okay? All right? And this is just some integral over the correlation function, so I haven't written out, maybe I should have provided that formula also for what is this in the halo model. It's just a particular integral over the power spectrum, but that's all. So you do everything to the power spectrum as before, and then you just do some integral. Okay? It's like instead of doing J0, you do, it's instead of a spherical Bessel J0, it's the full J0, that's all. Okay? But again, that's a technical thing. The main point is the clustering depends on luminosity. So then what was done? So then you say, I'm interested in modeling these galaxies. So I assume a cosmology, assume the cosmology gives me mass function, bias, NFW profile. And so now I just need to know what is the number of galaxies of this luminosity as a function of halo mass. And so that thing is varied. You try very many different shapes. And then finally, the shape that worked is this red one. And this red one predicts this red curve. You say, that's my best fit. So now I know the number of galaxies as a function of halo mass required to reproduce the data. Now I want to go and model these galaxies. Now I play with all the different ways. I can choose number of galaxies as a function of halo mass, and this choice makes that orange curve, which provides a good description. So you do this for each bin in luminosity. Okay? Really what they're doing is, this is everything brighter than a very bright limit. This is everything brighter than, this is the bright galaxies and a little fainter. This is those galaxies and a little fainter still. And this is all the galaxies. Okay, so they're doing everything brighter than some luminosity and changing the cut. Okay? And the result of doing that is that the number of galaxies as a function of halo mass is, this is all galaxies, this is little brighter, brighter still, even brighter still, to only the very brightest. Okay? And so this way, you've now modeled the measurements of the clustering. But now what can you do? Now you can say, suppose I fix a halo mass, 10 to the 14. Then at 10 to the 14 solar masses, I have 100 galaxies that are quite faint and above. I have 50 galaxies that are a little bit brighter and above. I have one galaxy, or I have 3 galaxies that are pretty bright and above, and I have very few galaxies that are super bright. So this is giving you the luminosity function at fixed mass. And so I can find out if the distribution of luminosities in massive galaxies is different from the distribution of luminosities in massive halos is different from in faint. But I can do that without ever identifying clusters, no? You just get it from this analysis. So I don't have to go and try to figure out, oh, this galaxy, is it in a cluster or not? It's difficult to tell because of the redshift space distortion. It's done, right? And so that means that now you're getting information about galaxies as a function of halo mass. So you're learning about galaxy formation from this. So you've turned clustering measurements into constraints on galaxy formation. So these are interesting for cosmology anyway, but they're very interesting for galaxy formation. Especially because galaxy formation models, they're having to decide how the baryons make stars. And so the galaxies making, the baryons making stars, everything depends on the potential well in which they're sitting. So and the potential well depth depends on halo mass. So all galaxy formation models work with what's the halo mass and what are the recipes for making stars inside halos of this mass. So this is the language they already speak. And so now you're able to pull out from clustering information what they should be getting. So now from this they can say, oh, the reason I'm screwing things up is because I'm implementing badly how to stop star formation happening in the massive halos. Or too many stars are being formed in the low mass halos in the model compared to in the data. They can start doing this. Yeah? So this is why this is a powerful approach. Yeah, it helps guide galaxy formation. Okay. That's not an obvious thing, that you could have done this so easily, and this approach shows you that it's straightforward. Okay. So then people, they usually estimate these by postulating some functional form and fitting for the parameters of that thing. Okay? And more or less it should be a step with something, and physically this 1 stands for the central, because you have to have one galaxy before you can have satellites. Yeah? And so most of these will parameterize the centrals and the satellites separately. The centrals will be the step function. What happened? The centrals will be this kind of step function thing, and the satellites will usually be some kind of power law. Okay. All right. So maybe I should stop there. Yeah. The rest is, if you know how many galaxies there are as a function of halo mass, so then the typical mass of the central galaxy is a function of halo mass. You can do efficiency of star formation as a function of halo mass. So you can do a bunch of galaxy formation this way. So there are some slides on here to show you that, but I will stop there for now. I didn't talk about all the other details that can be put in for different models, but obviously you can change the density profile of the halos. If you think it's warm dark matter, you think you're going to suppress the small scale cuspiness of the density profiles, you just put that in and get a prediction for how the effect there must be on galaxy formation, because you will change how galaxies populate halos. Yeah? It can be that you find that this is too steep, and that warm dark matter is predicting too shallow profiles, and so there's no way for it to get the clustering. So you can constrain the type of dark matter from the clustering signal by putting it in here. Yeah? So these are there are different things that you can do if you change the models, because it's very well defined what is changed by each input. Yeah? So it's a pretty transparent formalism for doing this. So it's a pretty active field because it lets you do everything. There's another one of these Yogi Berra quotes, this coach, right? Nobody goes there anymore because it's too crowded. So, and because it's useful for helping semi-analytic models, some people, they took the point of view that you don't need these models anymore because we will figure out how stars form in halos, and that's it. Okay? But that's not really correct, right? This is really just a means to an end. If I had a fast enough computer and I could simulate many different galaxy formation models, I would just do that very quickly and get the physical parameters directly instead of doing this roundabout thing. So this is a useful thing because we don't understand galaxy formation because the computers are too slow. Okay? But one day they will be fast enough, and then your parameters would not be what is the shape of this number of galaxies as a function of halo mass. You would just have whatever it was from the simulation. Okay. And what's happening is that people are trying to make ever more complicated models of how you relate galaxies to halos. And so the idea is the subclumps are the galaxies. But now the question is the subclump today related to a galaxy? Or, a lot of stripping happened to the subclump. And so maybe it was when the subclump fell in, then the baryons were already in its middle, and it has a dark matter halo. And it's the dark matter halo that is getting stripped away. But the gas is not stripped away. And so if I want a relation between galaxy property and subhalo, the satellite mass, then the relevant mass is the one before all the stripping happened. So now maybe I should be careful how I define my subhalos. But to do it properly, I needed to have kept track of more information from the simulation about how much mass got stripped when I do this. So people are doing this, and it's getting more and more accurate. But it's becoming more and more like a semi-analytic model, right? Which does exactly that. It took care of all the merging that happened as the process went along. And so there's a sense in which this approach is becoming a lot closer to the semi-analytics, in which case you should just do the semi-analytics. And so there was a fight in the field for a while, and so there's another Yogi Berra quote, which is pretty good, right, about going to funerals or not. And so, right, so there's increased complexity is blurring the difference between semi-analytics. But the HOD stuff, the halo occupation distribution, is still fine. And I think that's it. Yeah. One final quote, right? So this is especially if you're doing a PhD. Okay, so on these slides, you have the formulae you need. I think that review article has some of it. The stuff that's updated is the derivation of the halo mass function is a lot simpler here than there. There it's just given as fitting formula. And you only need a fitting formula, but it's good to have some idea of where it came from, especially if you want to do other things like merger histories and stuff like that. Then this approach is good. So you guys should feel free to contact me if you have questions, either going through the slides again or the notes, or if in the course of your theses you have questions that are using this stuff, you should just contact me. Yeah? Thanks. I know I went over in every single lecture, but I hope it was useful. And I think I'm done. Yeah.
Okay, so
all right.
Let's thank Ravi for all this. All the patience he had to discuss with you till late in the evening. So.
Yeah.